Okay, so now we want to turn our attention to a new coordinate system, the tangential and normal coordinate system. Remember, the Cartesian coordinate system was x and y, and they never changed. X and y never changed, but the normal tangential coordinate system is not so lucky. So let's assume that you're traveling on a pathway, just some arbitrary pathway, and think of your headlights. And so what we're going to do is we're going to think of green as the direction of your headlights. So your headlights are pointing in this direction, and they're pointing in this direction, and they're pointing in that direction, and they're pointing in that direction at these various positions. I could label them 1, 2, 3, and 4, and I may erase those in a minute. But that is the direction of your headlights. This is also the direction, you'll notice, that is tangent to the curve. And so what we're going to do is we're going to call that a unit vector, and your book is going to use U tangential with a hat over the top. I'm actually not going to do that because I don't like U. I'm going to use E. E tangential. And one of the things that you're noticing here is that E tangential, it's a unit vector, so it always has a length of 1, but E tangential is changing direction. I hat was always to the right. J hat was always up. Or you could rotate them for another problem, but however you set them for that problem, they were always in that direction. E tangential doesn't have that luxury. E tangential will change direction. Well, it turns out there's another unit vector, and it is normal to the curve. Normal, remember, the word normal means perpendicular. It's normal to the curve. And it turns out that E normal is always at 90 degrees to E tangential because it's perpendicular to the curve, and tangential is always parallel. But it always points to the inside of the curve. So one of the things you'll notice about E normal is that sometimes to go from E tangential to E normal, we go clockwise. But sometimes to go from E tangential to E normal, we go counterclockwise. And that's very different. This is not a right-handed coordinate system. In fact, it's not even a left-handed coordinate system. It changes as it needs to. But normal and tangential are always perpendicular to each other. Now again, if you think about your headlights always pointing forward, another thing that always points forward is your velocity. So the velocity vector always points in the direction of motion. Alright, so we've established in this coordinate system that there is a tangential direction. Label that with the green vector pointing in the direction of motion, and the normal direction. But the tangential direction is also the direction of the velocity vector. So the velocity vector points always in the direction of your headlights, which is tangent to the curve. Now the value of the velocity vector can be large or small, but it always points in the tangential direction. So in case number 1, the speed, remember the length of the vector is an indicator of the magnitude of the speed. Velocity 1 is medium, velocity 2 is large, velocity 3 is small. So medium, fast, slow. So the velocity vector then is always in the tangential direction. Now what that means is that the velocity vector is equal to some speed times the tangential unit vector. So the velocity vector is always in only one of those directions. We'll kind of look at this in a minute again later. All right, now what about the position along this motion? Well, the position is actually kind of interesting because let's say I'm here and I move to here. So I've gone through an arc length S. And this is the one time I really like S for position. But what you'll notice in this right-hand spot, this is along an arc length, and I use an arc length because it's on a curve, But that means then that that's a part of a circle. And the circle will have some radius. I'm going to call it rho 2 because I'm over here by velocity 2. We can call this S2. And this is rho 2 also because it's the radii of a circle. And we'll call this delta theta 2. Whereas if I'm over here someplace and I go through some S1, that circle might have a different rho value. Call it rho 1 and delta theta 1. The curvature will determine the radius. So one of the things that we know is that a tight curve has a sharp radius or a small radius, but a broad curve will have a large radius. So here's a small radius of curvature over here, large radius of curvature over there. So the radius of curvature can change depending upon the turn under which the curve is turning. All right, so what does that mean? Well, we know that S1 equals rho 1 delta theta 1. And as a matter of fact, let me call it delta S1. It's a displacement. It's a displacement. But keep in mind, arc length equals r times theta. But I'm not using r in this case. I'm going to use rho 1. I'm looking at a displacement, delta S, which undergoes a turn through the circle of delta theta. In this case, delta theta sub 1. I'm going to revisit that again here in just a minute. The other thing that we're going to notice then, as I look at this point right here, the velocity is forward. From v1 to v2, I am clearly increasing my speed. Now, I could have been increasing and decreasing between those 2 points, but let's just assume for a moment that the direction of the acceleration is the same. So what I'm saying here then is that there is an acceleration, a1, but that is speeding up the car. So notice the acceleration is in the same direction as the velocity. So the speed is increasing. When acceleration and velocity point in the same direction, speed increases. When acceleration and velocity point in different directions, opposite directions, speed is decreasing. But you'll also notice that I'm turning. And so there must also be a component of the acceleration in that direction. So we'll call that AN. We'll call this one AT. So the acceleration has 2 components. It has a tangential component, which not surprisingly is in the tangential direction, plus a normal component, which is in the normal direction. The tangential component changes speed, either increasing or decreasing. The normal component changes. So in the case of a car, the tangential component is either the gas or the brake. The normal component is caused by the steering wheel. Well, what I'm interested in then is the relationship between the tangential, the normal, and all of these other variables that we have to do with. Well, keep in mind that velocity is equal to speed times the tangential unit vector. Acceleration, by definition, and this is true in any coordinate system, by definition, that's the derivative of velocity with respect to time. Well, what do I have here? I have speed times the tangential unit vector. But remember, the tangential unit vector is changing the direction it points. Over here it points up and to the right. Okay, it's pointing in this direction. Whereas in position 2, it's almost only to the right. And in position 3, it's up and to the right again, but at a much steeper angle. Here in position 4, E tangential is down and to the right. All of these are E tangential. They're all the same length, but their direction has definitely changed. So E tangential is not a constant in time. I repeat, it's not a constant in time. And so when I go to do the derivative, I have to use the product rule. So the product rule says, take the first, multiply by the derivative of the second, E tangential with respect to time, plus the derivative of the first times the second. So there's the product rule acting on this velocity. But what is this? What is the derivative of E tangential with respect to time? Well, previous lecture, and what we found in the previous lecture was this is E tangential, and this is E tangential, and there's a delta theta in here. Oops, not delta Q, delta theta. Then delta E tangential with respect to delta theta, well, that was equal to another unit vector in there. Okay, E normal. So E normal is the derivative of E tangential with respect to theta. Remember, it was a unit vector perpendicular to E tangential. Well, that's going to be E normal. Well, keeping that in mind, then, the derivative of E tangential with respect to time is equal to the derivative of E tangential with respect to theta times the derivative of theta with respect to time. But the derivative of E tangential with respect to theta is E normal, and the derivative of theta with respect to time is omega. So the derivative of E tangential with respect to time is E normal times omega. So if I take advantage of that here, I get V times omega E normal plus the derivative of V with respect to time, E tangential. But the derivative of V with respect to time, that's going to be the change in speed. This one is the interesting one, though. V is the derivative of arc length with respect to time. But remember that arc length, S equals r theta, so the derivative of arc length with respect to time, that would be rho times the derivative of theta with respect to time. But that's going to be rho times omega. So V is rho times omega. So this becomes rho times omega E normal plus dV dt, which is the change in speed, E tangential. Well, this becomes rho omega squared E normal plus dV dt E tangential. So what does all this mean? Well, once again, this is the change in speed in the tangential direction. This is a change in direction. We've seen this before. Rho omega squared. Rho omega squared. That's going to be the same as, well, here we go. This is equal to V. Rho omega is equal to V. So this is the same as rho squared omega squared over rho. All I've done is multiply by rho over rho, which is V squared over rho. Or remember V squared over R. But what is that? Centripetal acceleration. Centripetal acceleration. So the normal component of the acceleration is the centripetal acceleration. And that makes sense if you think about it. What does centripetal acceleration do? It keeps you in a turn. And that's what this is. This is the component of the acceleration along the normal direction, the direction that's changed by your steering wheel. All right, so I can write this then as V dot, not V vector, speed dot E tangential plus V squared over rho E normal. And that's the acceleration in the normal tangential coordinate system.